So in our last lesson, we learned about the definition of lattice energy. So let me review a little bit about that just to get that picture in our mind. You have gaseous ions, and I want to use these pluses and minuses to represent ions that are in the gas phase. And they come together to make an ionic compound, which has this lattice structure that I'll use that to represent. And the energy released when this process takes place is called lattice energy. So it is an exothermic process when it releases energy. Now, a lot of times people think, why would it release energy as it comes together? And that isn't the easiest thing to grasp. But it is easy to grasp the opposite. If they are attracted together, okay, like little magnets that are held together, it requires energy to pull them apart. So doing the opposite process is endothermic. It requires energy to pull them apart. And we learned in our previous chapter that if you reverse the process, all you do is change the sign. So if it requires energy to get them apart into the gas phase, it would certainly release energy if you brought them together. Now, what the Born-Haber cycle is going to be about is determining the value of the lattice energy, because measuring it is not possible. You can't take ions and get them all in the gas phase and have them have no attraction for each other. Just say, hold it a minute, y'all are in the gas phase, and then say, okay, go, and allow them to come together and form this ionic compound and make a measurement of how much energy that requires to do that. So measuring lattice energy is not possible. So instead, we come up with a means by which we can calculate lattice energy, and we use this Born-Haber cycle to do that. Okay, we're going to construct a Born-Haber cycle for the compound lithium fluoride. I'm going to show you the components of constructing the Born-Haber cycle. Within there's a bunch of different energies that we can know in order to calculate the lattice energy that we don't know. So the process looks like that, like this. We're going to make lithium fluoride. So we're going to put lithium fluoride on the right-hand side as a solid, and we are going to start this Born-Haber cycle by making this from its elements. So what elements make up lithium fluoride? Well, we have our lithium, and lithium as an element is a solid. And we have fluorine, the element, which is a diatomic molecule. It's a gas. And I want to make 1 mole of this. So I want to keep it balanced with 1 mole here, so I have to put a 1/2 here. So the first step of doing the Born-Haber cycle is to make the ionic compound for which you want to know the lattice energy by starting with the elements. Now let's think about this energy for just a minute. In a previous chapter, we defined an energy, and here was its definition. Let's see if you can remember the energy. The energy change when you make 1 mole of a compound from its elements in their most stable form. What was that energy? You might even have to look back in your notes. Well, that energy was called heat of formation or enthalpy of formation. And we had a symbol for it, okay? It was delta H with a little f, and there's tables full of these in the back of the book. So that is our starting point of this, but there's no lattice energy in there yet. Lattice energy is taking ions and turning them into the ionic compound. This is my ionic compound. But what I don't have is gaseous ions, so I'm going to construct and make gaseous ions over here on the left-hand side. So the first thing that I need to do is I need to take lithium, the solid, and turn it into lithium, the gas. Now this is not the ion yet, so I don't have the ions yet, but I'll at least have it in the gas state. Well, there's an energy associated with that. What are we doing here? We're taking a solid and turning it into a gas. Is that endothermic, to turn it into a gas, or exothermic? Well, it's going to require energy to pull that apart into gaseous ions. This energy is called the heat of sublimation. Let me write it on this side. Heat of sublimation. Okay, there's an energy required to do that step. But now I've got the atom in the gas state. Let's take it one step further. I don't want the atom in the gas state, I want an ion in the gas state. So now I'm going to take the lithium and turn it into lithium plus the gas. Now, how do I do that? I do that by removing an electron. So let's think about the energy of that. Listen to the definition. The energy required to remove an electron from a ground state gaseous atom. What was that the definition of? That was ionization energy, and I'll abbreviate it IE. Okay, the energy required to do that. So now I finally have lithium in the gas state as an ion, which is the last thing I have to do before it can do the lattice energy release. Now let's get our fluorine where we need it. We need the fluorine to be in gaseous ions. The first thing we need to do is turn fluorine, the diatomic molecule, into fluorine individual atoms. Okay? So what are we doing here? We are taking a half mole of fluorine molecules where the atoms are hooked together, okay? And we're pulling them apart into gaseous atoms. There is an energy requiring you to, the energy required to break a bond. We have tables of those. They're called bond dissociation energy, or sometimes just bond energy for short. So there's the values of how much energy it takes to break that bond. Now we have a fluorine in the gaseous state, and we need to get it into a gaseous ion. So we're going to turn it into F minus gas. Okay, you know this energy as well. Let's look at the let's hear the definition, and you tell me what the name of this energy is. The energy change when an electron is added to an atom in its gaseous state. What was that? Well, that was electron affinity. Okay? Sometimes electron affinity is negative, sometimes it's positive, but that's electron affinity. We finally have the ions in their gas state. Okay? Now we're ready to get them to come together to form the ionic compound. There's my ionic compound. So doing this and turning it into this is our lattice energy, Le. Okay, so we've got all of those energies. Now, the Born-Haber cycle is an application of what we learned about in a previous chapter called Hess's law, and I think that's going to come up on our screen here. Okay, this is an application of Hess's law. Let's review in our mind that. We got an awful lot of reviews with this one little thing. Hess's law says that if you do a reaction in one step, the energy change for that one step, which is this step right here, and in our case it's called heat of formation, is equal to doing the same process in a whole series of steps. So let's number these energies. Let me call this one delta H1. And let me call this one delta H2, and we'll call this one delta H3, we'll call this one delta H4, and we'll call this one delta H5. What Hess's law states is that the delta H overall, which is the heat of formation, we'll put that underneath it, is equal to all of these other guys. We have delta H1, delta H2, delta H3, delta H4, and delta H5. That's the application of Hess's law. Whether you do it in one step, which is your overall reaction, or you do it in a whole series of steps, which there was 5 steps here, the energies have to be equal. Now we could go and we could look up in tables all of these energies. I'm handing them to you here. The heat of formation, let's get a value and let's put values in. The heat of formation is the overall process, and its value is a negative 594.1 kilojoules. Okay? The heat of sublimation, to take 1 mole of this and turn it into 1 mole of gas, is given to me there. It is 155.2. I'm going to leave off the kilojoules. No, I'm not. I'm not going to do that. I'm going to write them under so that they'll fit. Okay. Delta H2, that's the second one, is to break the bonds of the fluorine. The bond dissociation energy, it requires energy, is 753 kilojoules. Okay. Number 3, ionization energy. We're removing an electron. It requires energy to do that. It's 520 kilojoules. The delta H4, that is the electron affinity. Now, fluorine really wants that electron. Wants that electron so bad it will pay you energy for it, and so it is an exothermic process, a negative 328. Negative 328 kilojoules for that step. What we don't know is this one, which is the lattice energy. We don't know that one. So we know everything else, and we can solve for lattice energy. And that's what you use a Born-Haber cycle for, is in order to come up with lattice energy. Now, there would be a lot of variations that you would come up with for this if you did all kinds of different ionic compounds. Say, for example, we had magnesium reacting with oxygen to make magnesium oxide. Let's just talk a little bit about what kind of variations we'd have to have. Well, when you turn it into magnesium oxide, it is a magnesium with a +2 charge and oxygen with a -2 charge. So we don't just have to put one electron on or remove one electron like we do here. We have to remove two. So we would have two ionization energies. We're not just putting one electron on, we're putting two electrons on. So we have to have the electron affinity for both of those there. So there would be an example of a variation on this theme. So there's variations, and we'll practice setting up our Born-Haber cycle in class, but that's how you use one in order to come up with the values of lattice energy from this. Now, last thing I want us to focus on, well, not yet. Let's go ahead and, this is where we were. Let's look at what we see here. This lattice energy is always a negative value. It always releases energy to do this step. And that is what enables an ionic compound to form. Without this release of energy, this exothermic process, we would not have enough an ability to do these things. This requires energy. This requires energy. This requires energy. Even though lithium really wants to be a plus charge because it gives it a noble gas configuration, we are still pulling an electron off of an atom, and it requires energy to do that. So we have to overcome those energies. Some ionic compounds can't form, don't form, because there's not enough lattice energy to overcome crazy charges that we want to try to form. So you'd never have magnesium 3+ because there's not enough energy here to pull off a third electron off magnesium and make it a +3 charge. We'd only get a +2 charge because we know that when we reach in and pull that noble gas electron out from the noble gas core, it requires a crazy amount of energy. There's not enough lattice energy to overcome that. But for all the ionic compounds that we know and can be formed, it's the lattice energy that enables that to happen. So let's look at the Born-Haber cycle from kind of a different perspective. So let's go to the screen here, and let's kind of see that this is just another way of thinking about it, in which positive energies are going up and negative energies are going down. So we have a few negatives. And while this one is the overall reaction, okay? The overall reaction, and for this one we're doing a Born-Haber cycle of sodium chloride. So we're making the sodium chloride, and this is an exothermic process to take Na 1/2 of Cl2 and forming NaCl. Now this was a solid, this is a gas, and this is a solid. So that is the overall process. In this diagram, if it requires energy, we have an up arrow. So let's look at all of the different steps of the Born-Haber cycle. Okay, so we're going to zoom in a little bit here and see if we can get this to show us what's going on. The first step is to take the sodium solid and turn it into sodium gas. Okay, so we see that happening in the picture. Sodium solid is turning into gaseous sodium. That requires energy, and we call that enthalpy of, or heat of, sublimation. In the next step, we're taking chlorine, the diatomic molecule, and we see it here as a diatomic molecule, and we are turning it into gaseous atoms. So we're breaking that bond. We called that the bond dissociation energy. So that was step 2. These correspond to the same steps we saw before. Now what we're going to do is we're going to take sodium, the gas, which we see here, and we are going to take the electron off and turning into sodium the ions, which we see represented up here. So this requires energy, and that's ionization energy, to turn sodium, that's the purple, atoms into sodium ions. Then as we come over here, this step is to take the chlorine atoms and turn them into chlorine ions. Chlorine really wants that electron and will give you energy for it. So this is our first exothermic process. We finally have those ions, and we allow those ions to now come together and form that ionic compound. So we get it all the way down here into its ionic compound. That is the great release of energy. It releases so much energy, it makes up for all of these positive values and then some. So it is an exothermic process to make this sodium chloride. All right, so that is the Born-Haber cycle. We've got our Born-Haber cycle. Its goal is to determine what the lattice energy is. We know the definition of lattice energy, the energy released when you form an ionic compound from ions in the gas state. And we use this idea of thinking about an ionic compound formation as a series of these individual steps in order to calculate the value of lattice energy.